In the name of Almighty God, I am Master Sankoshi, and today I want to talk about resonance condition averaging over the oscillators. We seek to further simplify the main Hamiltonian based on the equation 53 so that we can analyze excitation transfer dynamics in this subsection. Before we introduce the resonance conditions, which assumes that the donor and receiver systems in groups alpha and beta have energy levels that are matched. This is the case in our example with deuterium helium 4 nuclei, which represents the same physical system in different states. We will need to keep in mind that this condition later when considering excitation transfer across different species of nuclei, for example between deuterium systems and palladium A systems as discussed in section 5.5 and onward. The electric field operator creates an or annihilates oscillator quantum, which means that the model under consideration couples to states that involve a different number of quantum. This can be seen by expanding out the Hamiltonian of equation 51 according to these equations based on the equation 54. This interaction involves the square of the electric field, which means that there is a coupling between states that differ by 2 0 and minus 2 oscillated quantum. Since we are here interested only in resonance processes, it is possible to eliminate the coupling to off resonance oscillator final states by taking expectation value over the oscillator degrees of freedom, yielding the equation 55. Thus, the model that results maximally simplified to include only resonant excitation transfer processes. Note that since in resonance excitation transfer no net change in the two-level system's energy results, the two-level system energy is constant. Note also that since there is no coupling to off-resonance terms of the oscillators, all of the basis state energies will be the same. This means that Hamiltonian zero oscillator will not contribute to the associated current dynamics, and that we can work with a Hamiltonian of the form where alpha beta is generalized Rabi frequency, which depends on the square of the interaction V. Equation 56 is now the simplified Hamiltonian, which describes the resonance excitation transfer between sets of many two-level systems. Note that no self-energy terms are included as we assume weak coupling within group R and beta. Approximate classical dynamics from the first theorem. We can now proceed to explore the current dynamics associated with cooperative resonance excitation transfer between two degenerate levels as described by simplified Hamiltonian equation 56 as discussed by Hegelstein in reference 87. F-force theorem can be applied as equations 58 and approximate classical evolution equations can be developed for this system. This yields equations 59, 60, 61, and so on. Nonlinear Rabi oscillations solutions to these equations are in general nonlinear Rabi oscillations based on their references 88 and 89, in which occupation probability periodically oscillates from ensemble alpha to the ensemble beta and back in a pulsed manner with a delay between pulses. It is possible to develop an analytic solution for a single excitation transfer pulse of this sort under conditions where the excitation is transferred from ensemble alpha to ensemble beta when the number of two-level systems in the two sets alpha and beta differ. Then we can write the equations based on 62 and also 62a. This results in a pulse like increase and decrease of decay enhancement whose shape is depicted in figure 12. The pulse length delta tau decay when the populations are mismatched is as a delta tau decay is equal to p divided by square root 12 square root h divided by absolute s to the power of r multiplied by h divided by absolute s to the power of b, where absolute s to the power of r divided by h is the initial population of group In our case, Na deuterium deuterium initially divided by 2. Note that for the highly idealized system that we have not taken into account decoherence or loose processes. You see figure 12, illustration of decay enhancement pulse in question 62, minimum and maximum decay factor based on the analytical solution equation to 62 and 63. We can estimate the maximum transfer rate tau maximum for a mismatched system to be on the other order of these equations based on 64 until 67. The decay enhancer factor assume its a minimum value at t is equal to 0 when the dynamics just start up. It then applies to the rate for the first transition. In this case, we can take MA is equal to SR, MB is equal to minus SB. And the expression simplifies to tau is equal to omega of beta square root 2 SR square root 2 SB. We can connect with the number of deuterium molecules and with the number of ground state helium 4 atoms according to 2 SR is equal to n deuterium. 2SB is equal to n helium 4. We end up with tau minimum is equal to omega alpha beta square root n deuterium square root n helium 4 for the minimum rate. For the second rate, we can take MI is equal to SR minus 1, MB is equal to minus SAB plus 1, which results in a rate tau mean plus 1 is equal to omega 2 square root n deuterium square root n helium 4. For the n transfer, we can take MI is equal to SR minus n, MB is equal to minus SAB plus n, which results in a rate tau minimum plus n is equal to omega n square root is equal to um, and etc. And now I want to go through the another section, transfer rate estimates, deuterium to helium for nuclei. In the previous part, the dynamics of excitation transfer were analyzed in the nuclear decay model, and it was found that excitation transfer in the form of nonlinear radial oscillations can occur between two ensembles of nuclei alpha and beta that are coupled indirectly to shared oscillators modes. In other words, excitation or rather, the occupation probability of excitation oscillates between groups A and B. In the subsections, a first rate estimate is provided for these process continuing with the earlier conceptual simple examples of deuterium donor systems comprising group A and helium-4 receiver systems comprising group B. At the end of this section stands a transfer rate estimates for excitation transfer based on each of the three couplings between nuclei and vibrational models to be considered in this context: magnetic dipole coupling, electric dipole coupling, and relativistic coupling. Because of this structure, this section can also contain a quantitative comparison of these couplings, yielding the insight that relativistic coupling is substantially stronger than magnetic and electric dipole coupling. An overview of this particular case of the nuclear excitation transfer is given in Figure 13, which shows explicitly the hindrance represented by the Coulomb barrier, part of the interatomic potential of deuterium molecule, which is represented by the expressions which the Gamow factor and which figure 14 illustrates the same process but emphasizes its time evolution, which includes traversal of off-resonance intermediate states per the discussion in sections 5.2. In the given state case, the gamma hindrance factor comes into the transfer rate expression twice, once due to the deuterium molecule transitions to the helium-4 state on the donor side, and once due to the helium-4 the nuclear transitions to the deuterium molecule. state. On the receiver side, this is not the case in the faster nuclear excitation transfer scenarios explored later in this case. For the scenario here, we will see that while the overall transfer rate is a function of several parameters and is therefore unable to change an acceleration more to the so then the spontaneous fusion rate, the predicted transfer rate is still too low to yield observable results. Nevertheless, the picture developed here will serve as an important stepping stone towards scenarios of greater stress, which are predicted to yield observable results introduced and discussed in the later sections. When evaluating obtained rates for nuclear excitation transfer, it is important to compare them with the expected decoherence times. If the mean transfer rate in a given system is longer than the corresponding mean decoherence time, then the system is unlikely to yield the observable results at a scale. Typically, qubits used in quantum computers, where the decoherence time is from microseconds to seconds, depending on the technology used. All operate at temperatures close to 0 Kelvin. The case of coherence between nuclei is quite different. On the one hand, nuclei interact much less with the environment, which has to do with the smaller size of their dipoles. However, since we consider nuclear systems across multiple atoms, such as in the case of nuclear wave functions of the deuterium molecules, special degrees of freedom, which includes a molecular dissociation and angular momentum changes, had the potential to disrupt coherence and make it as a decoherence. As shown in section 6.22, we expect a mean decoherence time of about 1 nanosecond. Another decoherence mechanism is spin relaxation, which is however much slower than the molecular dissociation. A proxy for spin relaxation in the system of interest is provided by nuclear magnetic resonance experiments. In the study of the deuterium spin relaxation in metal deuteride at room temperature, there are two time parameters of interest: T1, which is measure of the longest lifetime associated with the spin correlation, and T2, which is a measure of the shorter dephasing time. A typical value for spin dephasing of hydrogen in a palladium is 10 milliseconds at room temperature based on the reference 90. So we can expect the same order of the magnitude for deuterium or helium. For now, we will adopt a decoherence time on the order of 1 nanosecond. The later sections 5.8 considers this kind of decoherence as an explicit constraint, which an excitation transfer process needs to exceed for it to yield observable results. In that section, the basic experimental parameters will be given under the which the predicted transfer rate does indeed exceed the recurrence time. Sections 5.8 will build on sections 5.5, which contains an extended variant of the model applied here. Figure 13 illustrates the resonance-nuclear excitation transfer of 23.85 megaelectron volt from the deuterium and tends to helium-4 fusion decay to the helium-4 tends to deuterium excitation. We consider two ensembles are nuclei alpha and beta, whereby ensemble A denotes the group of deuterium nuclei in the coupled system which can undergo the deuterium it tends to helium-4 transitions, and B denotes the group of helium-4 nuclei in the coupled system which can undergo the helium-4 tends to deuterium transition. The collective transitions of group of all occurs coherently together with the corresponding transitions in group B. Note that in actually this kind of excitation transfer process involves pathways through different possible intermediate states, exhibits an asymmetry in how they are affected by loops represented by N in figure 14. So figure 14 illustrates resonant nuclear excitation transfer between a deuterium-deuterium for the NOR transitions and deuterium helium 4 receiver transitions by indirect coupling via a shared oscillator mode. Destructive interference between the upper and lower intermediates, for example, visual states, is reduced by the selective loss in the lower pathway, allowing for the resonance nuclear excitation transfer to occur, here represented by N per section 6.5. Recalling the expressions for the excitation transfer rate, the derivation of decay factors in 6.12 yields expressions for the minimum and maximum rate of excitation transfer following equation 65. 9 in the minimum rate is as the equations in 73 and 74, 75 were notation wise. We added here a subscript to V to highlight when a generic coupling is referred to rather than a specific one for the transition considered in this section. As shown in figure 13, a generic coupling a V generative is represented as follows. Since as well we'll see shortly, the gamma factor term e to the power of minus g can be explicated as a key factor in all of the indirect coupling terms intersections where U0 differs based on the nature of the coupling, for example, electric, magnetic, and relativistic coupling. Note that for that calculations under realistic conditions, we need to work with realistic loose scenarios instead of ideal loose. Therefore, pair equations 53, we bring in again and corrections factor absolute 1 minus n in this case twice, because for excitation transfer from distribution to helium 4, non-ideal loose occurs at the donor and the receiver's side C6.5. For being able to use these simple versions of minimum and maximum decay factors, we need to assume that there is a greater number of receivers helium 4 systems than donor deuterium systems. Concretely, we consider a uniform oscillator mode in palladium spanning 10 to the power of 18 unit cells corresponding to a volume defined by a mode frequency in a megahertz range. In this volume, we then consider to be present and a deuterium is equal to 10 to the power of 15. Donor systems representing group A and Na helium 4 is equal to 10 to the power of 16. Receiver systems representing group B. This then results in a ratio of Na deuterium divided by N of 0.001 and N helium 4 divided by N of 0.01. All nuclei in group A and group B are uniformly coupled to the same oscillator modes per the discussion in sections 5.1. Most physical metal hydrogen systems will not exhibit such high helium content, although they can be prepared this way by, for example, loading the metal lattice with helium in addition to deuterium. Note also that there is a helium content on the order of the 1 picometer is natural air in, and we can expect some helium to be present in all metal lattices. That being said, the assumptions of a large number of helium-4 nuclei made here for pedagogical purposes, as we will later in sections 5.5 and onwards consider a case where the receiver systems are palladium nuclei, which are indeed greater in number than deuterium pairs in palladium deuterium systems. Next, the Rabi frequency will be evaluated for the three couplings available: magnetic dipole coupling, U magnetic and electric dipole coupling, U electric and relativistic coupling, U relativistic, a magnetic dipole coupling. For the magnetic dipole coupling, the indirect coupling strength between the deuterium helium 4 donor transitions are assumed to start out in the exotic states. For example, deuterium and deuterium helium 4 receiver transitions are assumed to start out in the ground states, for example, as helium 4 per the nuclear excitation transfer model discussed in sections 5.1 and 5.2. So thank you so much for watching my tutorial video until the end. If there is any simulations for this literature, you can find it from my github.com/masterscript, github.com/kashi script or /Safra script. Today is the 7th day of July 2026.